Okay, so here's the first question from the No Brain Too Small linear mechanics collated questions. So the first one talks about rockets being launched by Rocket Lab up on Mahia Peninsula in Hawke's Bay, and the rocket can carry a satellite of 1.5 times 10 to the 2 kgs to a stable circular orbit, and then there's this 20 kg piece of space debris travelling in the same altitude and speed as the satellite, but in a direction that is at 90 degrees to the satellite's velocity. At the moment shown in the diagram, the debris of the satellite is 1.08 times 10 to the 4 metres apart, and the satellite is travelling at 7.61 times 10 to the 3 metres per second. So here's the scenario drawn out here, and I just realised in reading that they're actually going at the same speed, it says. So this here must also be 7.61 times 10 to the 3 metres per second. Great, so for the first question we need to calculate the distance between the centre of mass of the system and the satellite. So the centre of the mass of the system must be somewhere along this dotted line. It does say distance, so I don't need to work out the angle. I'm just working out how far along this line it is from the satellite. And we need to describe the motion of the centre of mass of the system and justify that. So for the first question we're going to work out the position of the centre of mass using this equation, and because the question states that we want the distance from the satellite, I'm going to use this, the position of the satellite, where I take all of my displacements from. So M1, that's going to be the satellite, so I'm going to use the mass of the satellite here, and because I'm taking all my displacements from the position of the satellite, that's 0. The satellite is 0 meters from the satellite. Then up here we've got the mass of the debris and its position. Well, it's the full distance. So it's 10 to the 4. Cool. And then we're going to divide that by the total mass of the system. Cool. And we're going to put that into the calculator now. Oh no, there it is. I was concerned that I didn't have my calculator. Right, now I use excessive brackets when I enter things into calculators. It just makes it a bit more likely that I'm going to get the right answer. Obviously I didn't need to enter this because it's multiplying by 0. Make sure when you are putting in a number that's in scientific notation, use the EXP button on your calculator. You're less likely to make a mistake that way. 2 plus 20, there we go. 1,270. What are these all? These are all to 3dp. We'll ignore the 20 kgs, so let's go with that. Meters to 3 significant figures. Sorry, I meant to say significant figures earlier. Cool, so let's see if that's reasonable. So this is 10,000 meters here, roughly, and this is 1,000/10th of that. Yep, so this has got majority of the mass of the system, so I'd expect it to be much closer to the satellite than to the debris. So this looks like a good answer. Alright, moving on to the next question. The debris collides and becomes embedded in the oh wait, I didn't do the second part of this question. Describe the motion of the centre of mass of the system as the debris and satellites continue to move along their paths, and justify your response. Well, the motion of the centre of mass will be at a constant velocity, and the way I can justify that is that there are no external forces acting on either of the objects, so that means the centre of mass of the system must travel at a constant velocity. Then for D here, the debris collides and becomes embedded in the satellite. Calculate the speed and direction relative to the initial direction of the satellite, and the embedded debris. Okay, so this is probably a conservation of momentum question. So basically, the total momentum at the start is going to be equal to the total momentum after the collision. And because both of the objects are stuck together after the collision, that is the momentum of the system. Didn't explain that very well. Whatever. Let's go on to 1D. So what I need to do basically is work out the total momentum before the collision. Now the important thing to remember is that these are vector quantities. Okay, so I can't just add them up as if they're scalars. So I need to take their direction into account. So I'll draw them in correct colours, and I'll use red to represent the total. So the momentum of the satellite is in this direction before the collision, Psat, and that's equal to mv. So the mass of the satellite is 1.5 times 10 to the 2 times the velocity of the satellite, which is 7.61 times 10 to the 3. Cool, and if I put that into my calculator, um, 1.1415 times 10 to the 1, 2, 3, 4, 5, 6. Cool. The momentum of the debris is going to be much smaller because the mass is much smaller. So P deb mv, and its mass is 20 times its velocity, 7.61 times 10 to the 3. 20 times 7, 1, 5, 2, 2 times 10 to the 1, 2, 3, 4, 5. These are both in kgs, meters per second. Right, and then the total velocity, sorry, the total momentum of the system is this here. P total. So this is how we work out the momentum of the system before the collision. But if there's no external forces acting, and there won't be in this scenario, this is going to be the total momentum after the collision also. So the way we need to do that, this is a right angle triangle here. So we need to work out the length of this side. So that's the square root of P sat squared plus P deb squared. So that's, oh my gosh, what have I done? I've started doing it all in these different colours. It's going to take forever. Times 10 to the 6 squared plus, my square root's not going to be long enough, man. 1.522 times 10 to the 5 squared equals, right, bung all this into my calculator. Just going on about excessive brackets, and then I don't use excessive brackets. Oh no, I need to get it into insert mode. 1 point, there we go. Plus 1.522 to the 5. Okay, there we go. What have we got? 1.423 times 10 to the 1, 2, 3, 4, 5, 6 kg meters per second. Oh yeah, 4 significant figures. No reason for that. Alright. Cool. And I'm just going to have a quick look. It's pretty close to this value, but it is bigger. And that's kind of what I'd expect, because this momentum is so much smaller than this one. It's kind of insignificant. But it does make the total momentum slightly bigger than the momentum of the satellite. So this is a good answer. Cool, then the second thing we need to do is work out the angle in which they're travelling in relation to the original direction of the satellite. So that's this angle in here, theta So to do that, we need to do a bit of trigonometry. I'm going to avoid using this side. I'm going to use the two sides that require less calculation because I'm more likely to get the right answer. So that means I need tan theta. So tan theta equals P dep over P sat, and I'm going to change pens because that one's impossible to read. Which means theta equals tan to the minus 1 P dep, which is 1.522 times 10 to the 5 over 1.1415 times 10 to the 6. Cool. And then putting that into the calculator, we get check that you've got your calculator on the right units. I guess there aren't really any right units for degrees. Any of them will do. Sorry, for an angle, any of them will do. Just means that you're going to be writing your answer to the correct unit. 3 significant figures. Cool. And again, because the momentum of the satellite is so much more than this, I'd expect this to be quite a small angle, and 7.6 degrees is pretty close to a small angle. Cool. I'll move on to the next question now.